Today we're not just going to cover the same exact stuff that you've already heard on magnetism. You saw the episode of Bill Nye, which we'll watch a little bit of that again today. You read the handout, some of you more carefully than others. And some of these terms are the same, and we're going to cover them again, and I'll explain it a different way, but some of it's going to be new information. And I want to point out to you, some of you mistakenly think that if you copy down the terms and you get the definition for the terms, you've done all you're supposed to do for your notes. That is not always the case. In fact, the biggest concept today, what is magnetism, isn't written up there. Okay? You're going to have to get that concept either, if you got it in your head, great, you don't have to write anything down, but if you don't, you're going to need to write down a description of that, some examples that will help you to understand what magnetism is. And yes, we are going to get to our essential questions there in a little bit. Before we do that, since some of you are still copying that down, I want to show you a quick little demo here that has to do with static electricity. In honor of Ben Franklin's birthday, which it is today, a lot of you know that he's famous for a lot of his politics and being a founding father, and of course being a president. Remember when he was the president? Remember that?
No.
He wasn't the president, exactly. A lot of people think Ben Franklin was a president. He wasn't. But he was involved in politics, and he was involved in science, more than a lot of people realize. He was an inventor. And in addition to the famous experiment with the kite and the key, which is often exaggerated, he did invent the lightning rod, which helped us build taller buildings that wouldn't get burnt down by strikes of lightning. He invented a stove known as the Franklin stove, and many other devices. But one of the ones that people haven't heard of is the Franklin bells, which I have up here. And it was real hard in those days to find Diet Coke cans, but he did find some Diet Coke cans to make his Franklin bells out of. There were no Diet Coke cans. But what they were, what this device was a device to warn you that lightning might be in the area. So you could run inside, get out of the pool, whatever the case may be. And he had two bells, and they were mounted onto like a wood base, and one bell had a wire, you can see it here with the green wire, going to a rod that went into the earth. A grounding rod, we say. I'm using this connection on my Van de Graaff generator. The other bell went to a wire that went to a pole that went up into the air, like a lightning rod. And the idea is that one of those bells would gather up charges that would be developing in the air near the clouds, would be developing, and those charges, those electrons, would then travel down through the wire. And if you know the rules for electrons, you can understand how this works. And you can anticipate what's going to happen when I turn it on. What's going to happen? The electrons are going to want to get to this one, right? You remember that as one of our rules? Electrons want to go to where there are fewer of them. Electrons want to go to the ground, okay? Well, it's difficult for the electrons to jump from this can to this can, or in the case of his bells, from one bell to the next, because they're still separated by air. But what he did is he put a little clanger in between, a little piece of metal. In my case, it happens to be this little, the pop top, okay? And I've hung it from a thread. And that pop top will serve as a conductor, kind of like a shuttle bus, to carry the electrons from one can to the other, or in his case, one bell to the other. So, we think about the charges and where they are and where they're going to want to go. We're going to build up a lot of electrons here, like we would in the cloud. They're going to travel down the wire and they're going to build up on the can. We would say the can is charged, and they want to get over here. If I have a bunch of negative charges, what do you think the charge is going to be on this little pop top that's hanging from a thread?
It's going to become negative.
But what is it going to be before that?
Neutral.
Neutral. It's going to be neutral to begin with, and it's then going to be attracted to the can. Because the pop top is neutral, the can is negative, they're going to be attracted because the electrons are going to want to get to the pop top. Pop top's closer than the other can. So once this travels over to this can and touches it, what charge does the pop top get?
Negative.
Negative. Do you think it carried away all the electrons from the can? No. Not only is the can bigger, but it's got a constant supply of electrons coming from the air. So the electrons then, some of them are transferred by the pop top, and they now want to go where? To the other can. What's the charge on this can? Neutral. So the negatively charged pop top will want to go over here to carry the electrons over. In addition, because this can is negative and the pop top is negative, they're going to repel, which is the answer you should have put on one of your questions for the homework today. Like poles, like charges, repel. So it pushes it over here, this touches this can, it drops off its electrons, and they go into the earth. Is that the end of it? It's just going to go ding, and that's the end of it? It's going to come back. It's going to get another supply of electrons. It's going to touch it again, charge up, and then go back. So what you end up with is this little clanger is going to keep going back and forth. Head up, Sky. It's like a shuttle bus. You guys know what a shuttle bus is? You know, like when you go to the baseball field and they pick you up and they take you to the Arizona Stadium for a football game. And then they come back and they pick up another load of people and they keep doing it until everyone's over there. Well, this little pop top is not going to be able to carry too many electrons. So it's going to come over here and say, okay, electrons, jump on. And they're going to fill it up as much as they can. And then it's going to be repelled. It's going to drop them off over here. And then it's going to be attracted to it again. It's going to charge up again. And then it's going to drop them off. So it keeps dropping off loads, if you will, of electrons. So the little clanger goes back and forth. Back and forth. Okay? I got this working a lot better now. We'll try it again on another day. But this will really crank out the electrons now. And of course he had bells, and so it's going to be ringing. Pretty cool invention. The Frank tracked it to... I'm just joking, of course. Electricity is...
The flow of electrons through a circuit.
A circuit is? Electrons come from?
Atoms.
Okay. Who can give me 3 ways to get electrons to flow? Chemical reaction in, say, a battery. If you give it a path, and? So simple, a caveman can do it. Not just any rocks, quartz, okay? And there's many other examples, guys. Those are just the ones we talked about. In fact, magnetism plays a big role in making electricity. We'll get into that next week. All right, so we haven't really answered how they're related, but you should be able to tell me what causes magnetism. Magnetism is caused by blank, blank. Blank, blank on the atoms. Unpaired electrons. Again, that term and that concept is not up here. Okay, it doesn't say unpaired electrons, because I don't want you just to define unpaired electrons. I want you to understand, when we're done today, how unpaired electrons results in magnetism. Why everything that is made of iron, nickel, and cobalt isn't already a magnet. How it becomes a magnet. That's the main concept today. We know that in current electricity, we look at the voltage, current, and resistance. Voltage would describe the what if it were water? Pressure. Current would describe the rate of flow, the number of electrons every second. If we add resistance, what's going to happen to the current? It's going to slow down. It's going to go down. 3 ways. Who can tell me 3 ways to increase the resistance of a wire? Zach?
Change the diameter.
Make it smaller.
Material.
Change the material to something with more resistance. And make it longer or shorter?
To what?
To make it more resistance.
Longer.
Longer. The longer the wire, the greater the resistance. So obviously if you add resistance and it changes the current, that shows you how they affect each other. The rule, the law, is called Ohm's law. V equals I times R. Good. Lynn remembers. A battery produces electricity through a between 2 and 1 electrolyte. 2 electrodes and 1 electrolyte. Okay, so those are the basic questions everyone should know. I may not define these exactly in the order you see there, but it'll be pretty close. Okay, we're going to start with looking at electricity way back in the beginning. I'm sorry, magnetism is what I meant to say. But before we do that, I just want to make sure you appreciate magnetism, because a lot of people mistakenly think magnetism is all about, just these little permanent magnets and playing with little bits of iron. Who they stick together, who they push apart, and that's just a toy. And that's where magnetism ends. Or maybe these little guys. You throw them up in the air. Seen these before? Yeah. They make that little squeaking sound. Okay. Magnets are not just about toys. You have magnets probably on your body right now. You may even have magnets in your body right now. We'll talk more about that on another day when you learn how birds use magnets in their brains. Lobsters use magnets to navigate. But you have magnets in your body most likely right now, or on your body, if you have a cell phone. Cell phone has speaker. The speaker uses a magnet. Without the magnet, it doesn't work. Plain and simple. So anywhere you've got a speaker, you've got a magnet, you're using magnetism. The headphones have little miniature speakers. They have magnets. They have a motor that spins the CD around. That requires magnetism. A blow dryer requires magnetism. Anything with a motor, a fan, your washing machine, dryer, air conditioner, all require magnetism. The computer greatly depends on magnetism. The speakers have magnets. This type of monitor has magnetism that controls the picture, which is why you're not supposed to take magnets and bring them near that kind of monitor. The hard drive inside, like this one here, uses magnets to spin it, also uses magnetism to put the information on the hard drive. Okay? Magnetism is so important, it's so basic, that you wouldn't be able to see me now if it wasn't for magnetism. Light requires magnetism in order to go from one point to another. That's how basic this is. And we'll look at that part later on. But today, let's go back in time. I don't know why this isn't responding to me. Let's go back in time to our earliest understanding, not working again, of magnetism, which is at 900 BC. I'm going to tell you a story that may or may not be completely true. It's one of those legends that's been passed down over the years. And this story takes place outside the Greek town of Magnesia. In 900 BC, there was a shepherd, and he was tending to his sheep, and as he was walking over the black stones, he noticed that the tip of his staff kept getting stuck in or on the rocks. Legend has it that the tip got pulled right off the end of his staff. And the iron nails used to hold his sandals together also got pulled out. His sandals started to fall apart. Okay? That's the legend. It's probably not completely true. It's like those fish stories, I catch a fish and it's this big, and I tell my son, and he tells his friends, and it becomes this big, and so on until 3 generations from now, I caught a whale. And it was only a little fish. Well, the guy probably didn't have his staff pulled off, the tip pulled off. He probably didn't have his sandals come apart. But what he did probably happen upon is these peculiar rocks right here called magnetite. And it's named magnetite after the Greek town near which they were first discovered, Magnesia. Magnesia is the town near which the first natural magnets were discovered. Magnesia is the Greek town near which the first natural magnets were discovered. Magnesia is the Greek town near which the first natural magnets were discovered. The whole rock is the magnet. It's a naturally occurring magnet, a naturally occurring magnetic material known as magnetite. Magnetite is the scientific name. course, most things have a scientific name and a common name. You know, you might call it your upper arm bone, but we know the real name is humerus. You might call it a dog. The real name is Canis familiaris. Familiar dog. Felis domesticus. House cat. Yeah. So we have a scientific name, and then we have the common name. Lodestone is the common name for that rock. And as you can see, it's not a very powerful magnet. You can see the little bits of iron holding on to it. But it's enough that you can feel this effect. You can see that there's an attraction to it that's unique to that rock. Lodestone is the common name for this material. Now, my theory about what happened next is just a theory. It's not based on any fact. I'm guessing that the person that first discovered this took the rocks back to town and showed some people, and they just all imagined that the rocks must have some magical properties. Good job. I doubt this story. We certainly can't imagine that these rocks are powerful enough to pull the iron nails out of the sandals. I suspect a more likely story is a couple kids were outside of town having a rock fight. And they went to pick up a rock and realized it was kind of sticking to the next rock. And they looked at it and they go, there's no glue, they're dry, what's making them attracted to each other? They didn't understand why or how they worked. Probably took them back to town and charged people money. I'll let you see my magic rock if you give me $1. Okay, and show them the rock. Or maybe they try to convince people that these magic rocks that things stick to have magical properties. And if you've got a headache, Matt, I'll just rub your temples with my magic rock and it'll make the headache go away. Or if you keep it in your pocket and you get, your stomach is upset, you can hold it to your stomach and it makes the pain go away. Or maybe you can hold it to your wrists and it will improve your circulation. Sounds pretty ridiculous, huh? Believe it or not, this was the belief in the 1800s in this country. People were selling magnets as a way of curing all sorts of illnesses. Big old belts that had magnets in them that were supposed to make you lose weight. And a lot of people believed it. They didn't really understand how magnets work, what magnetism is. Once you understand that, it's a little bit easier to test this stuff scientifically. Even today, we're still selling things. We're selling things that go in your shoes with little magnets, bracelets with little magnets, and things like that that are supposed to improve your health. Maybe it'll turn out that they do, in fact, have those effects. But right now, not a lot of studies to support that. So all we knew is that these things have magnetic properties. And nowadays, we can analyze those rocks, and we know that they have certain chemicals in them. And my board's not working, so I'm going to have to write it up here like this. The chemicals, as you see from your notes there, that go into magnetite or lodestone are Fe3O4. Now I ask you to get out your planner because it has this periodic table. Turn to page 139 in your planner, towards the very back. That way you don't have to squint to see this one. And you'll see a periodic table. Can somebody locate the element Fe? Brianna? It's iron. Number what? 26. 26. Somebody locate the element O. Zach?
Oxygen.
Oxygen. Number 8. So here's oxygen, and you saw iron there. Okay? Now, I'm often asked, why do they make this so confusing? Why do they use Fe as an abbreviation for iron instead of I? And the answer is 2 parts. One, I was already taken by what? Iodine over here. Already has the I. The other one is, you got to remember, not everyone speaks English in the world. In fact, the language of science was Greek and Latin. And these words often come from Greek and Latin words. The word ferrous, F-E-R-R-O-U-S, or ferric, means with iron. Okay? So the legs of your desk are ferrous. They actually have iron in them. They're not pure iron. They have iron and carbon. We have iron and carbon together, we have something called steel. And that's why magnets stick to so many things, because a lot of stuff around the house are made of steel. Okay? So those are some common elements. Now you might also notice here that there are others that have unusual abbreviations. What's the abbreviation for gold?
AU.
AU, number 79. And for silver? AG, number 47. Okay? So again, we can't always use the letter you think. Silver can't be S because that's already taken by sulfur. It can't be Si because that's already taken by silicon. So we use a Greek or Latin word as the abbreviation. Fe is ferrous, Fe means iron. Okay? There's plenty of ones that do line up that make sense, H and He and so on, but others like mercury, Hg, might seem unusual. There is a reason for that. Not everyone speaks English. Okay? When you're done taking chemistry in high school, you'll be quite familiar with the periodic table and you'll know what all those abbreviations are. But the reason I wanted you to look at this now is I wanted you to see that in order for that rock that I gave you to be a magnet, to have the ability to be a magnet, it must be made of one of three things: iron, cobalt, and nickel. Notice how they're all next to each other right here on the periodic table? Those three things can all be made into a magnet. Okay? Alright, so we got this magic rock. Things seem to stick to it. And I'm going to give you the definition for magnetite here in a little bit. Things seem to stick to it, but what use is it? Well, eventually someone did figure out a use. They realized that if you hung that rock from a string, that it would always spin and point in one direction. They made the first compass. If you balance it on a little pinpoint, it'll also spin and point one direction. So that was probably the first use, real practical use, not just conning people, of magnetite to make a compass to help you sail. Yes?
How would you know which point is going to work?
You mark it. You mark it.
Oh, okay.
Put a little mark on the rock itself, or maybe even shape it so that it's more like a bar magnet. Break off some pieces until it's more like a bar magnet, and then it's easier to tell which direction it's pointing. This one. Okay? So that was the next step. Now we have to jump ahead, way ahead in time to 1600 AD. In terms of history, not that long ago. It was a great time in history when guys got to wear collars like that. You know? Doesn't that remind you of what you put on a dog when they have surgery and you don't want them to lick themselves? So let me tell you about this dude. This is Sir William Gilbert, and he was the Queen's personal physician. Queen Elizabeth of England had a personal physician. Our president had a personal physician. This guy's only job was to tend to Queen Elizabeth when she was sick. So assuming she wasn't sick all the time, he had a lot of free time on his hands. And during that period of time, there weren't a lot of people with college educations. And there weren't a lot of scientists like there are today. So it wasn't unusual for someone that had gone to college to, as a hobby, do their own little science. They might try to come up with an invention in their home, or work on science experiments in their home to just try to answer some basic questions. And that's what Sir William Gilbert did. This wasn't his field, he was a doctor, but he did do some simple observations. Head up, please. And what he did was very basic. As are most of the big discoveries in history, they're not someone that totally comes up with something completely new. All they usually do is take a couple ideas and put them together that are already out there. What we knew around this time, we knew that the world was not flat. We knew that the Earth was a ball. And we also knew about magnetite, that how it would spin and point in one direction. What Sir William Gilbert did is he started to play around with a sphere of magnetite, dropping little iron filings on it, and noticed that there were two opposite areas where they wanted to stick on the most. He had a ball of magnetite, and he saw two opposite areas with the strongest attraction, known as the north and south poles. And he got to thinking, this is a ball of rock, a sphere of rock, that has two areas of opposite attraction. Okay? They either attract or they repel. And when we use it like a compass, it always wants to point in one direction. To what? Maybe it's pointing to the Earth. Maybe the Earth is like this ball, and it's a giant magnet. So he was one of the first ones to say that the Earth has a magnetic field. For Sir William Gilbert, he is the Queen's doctor who experimented with a sphere of magnetite. The Queen's doctor who experimented with a sphere of magnetite, I'll get you in a second, and suggested that the Earth has a magnetic field. The Queen's doctor who experimented with a sphere of magnetite and suggested that the Earth has a magnetic field. Queen's doctor who experimented with a sphere of magnetite and suggested the Earth has a magnetic field. And I know you haven't gotten the definition for lodestone or magnetite yet. We'll get to that in a second. Question?
Yeah, could you make the compass point south?
Sure. Well, a compass, when you think about it, a compass does point south.
Yeah.
We just labeled one in red, right? And the other one we didn't label, so we go with the red one. But if I labeled the other in red, then it would be pointing south. Absolutely. Okay? Uh-oh. Okay, gremlins. Okay. So that was Sir William Gilbert. And that was a big step forward because now, instead of it just being some magical rock that does something on its own, we don't know why, we're starting to connect. We're starting to go, the Earth has a north, the Earth has a north and south pole, and the rock has a north and south pole. And the reason that rock turns and points one direction is because the South Pole is attracted to the North Pole, or the North Pole is attracted to the South Pole. That's what he was saying. He was explaining how this works. We still didn't know why the Earth was a giant magnet, or how it became a magnet, but we were able to at least explain a little bit of why it's working for us, why it always points that one direction. And what we know is that the Earth rotates and it has liquid metal inside that also rotates. And that liquid metal contains iron and cobalt, or iron and nickel, in a way. But it contains magnetic material. And when that magnetic material is moving, you've got magnetism. When the electrons are moving, you've got magnetism. That's the real secret. We'll get back to that later. But if you look inside the Earth, you see this liquid metal core that's moving around constantly, and that's creating the magnetism. Not every planet has that molten center that is moving, so not every planet has a magnetic field, as you heard on Bill 9 yesterday. Okay? Now, I showed you some of the magnetism that surrounds a typical bar magnet. I didn't show you what happens when we put two together and we sprinkle the iron filings. But this is simply to show you that a north and south pole brought near each other with some iron filings sprinkled on top will show an attraction. And that's what the iron filings are doing. They're lining up with those magnetic lines of force. Now at the bottom, unlike poles brought next to each other, will repel each other. The filings are still attracted to each of the poles, but in between, we don't have the lines of force. I'll show this to you again up here, because this is important that you remember this and can visualize this. Every time you look at a magnet, instead of just saying, oh, they want to stick to each other, you should see that and picture the lines of force that I asked you to draw on the homework. Remember how they went out like this, and they curved around and tried to get back to this end? Remember that? I had some people on the homework today telling me that the South Pole is stronger than the North Pole. Is that true? No. They're opposite. The poles are opposites. And your definition for the North and South Pole should say two zones of strongest attraction or repulsion on a magnet. Two zones of strongest attraction and repulsion on a magnet. They're on opposite ends, and if we get two souths together, they're going to repel. A north and a south, they're going to attract. And those are the words you should have used on your homework. What do like poles do? Like poles repel. Do unlike poles do? Attract. Those are the words you should have used. The two zones of strongest attraction and repulsion on a magnet. So from now on, when you look at one of these, you're picturing what we call the magnetic lines of force. And here you can see, as I sprinkle it around the outside, how those little bits of iron will want to line up with those lines of force, and how more bits will collect near the poles. This is what your illustration should have looked like. And I'm going over all this stuff in the event that you got things wrong. You can fix it before we grade this in class. Oops. Okay, so your picture should look something like that. Now, of course, my little bit of transparency here is letting them slip, but you can see more iron filings here. They even stick up off the page, and fewer as we get farther away. So if I ask you to make a generalization about what's happening, you would say that the magnetism is strongest the closer we get to the magnet. It's weakest the farther we get away. It's strongest near the poles and weakest here in the middle along the side. That's the weakest part. It is as if the magnet's trying to bend itself in half so that the north end can bend over and touch the south end. But every magnet, regardless of whether it's a bar magnet like this one or a horseshoe like the next one I'm going to show, will have that invisible field of attraction that surrounds it. That invisible field of attraction that surrounds the magnet is called the magnetic lines of force. I'll repeat that for you, for your notes. The invisible field of attraction that surrounds a magnet. That's the magnetic lines of force. The invisible field of attraction that surrounds a magnet is the magnetic lines of force. Again, when you see a magnet, you should picture those lines of force. Right now, they're going right through my thumb and finger. And they're going out like this and coming back here. And if I were to put something here, I know exactly where the lines of force are and how it would influence it. In a horseshoe magnet, all we've done is taken a bar magnet and bent it in half. Yes?
Are the poles on a bar magnet exactly in half? Like if the north and the, are they exactly?
Does it just stop from going north to becoming south? Is that what you're saying? That's a tricky question to answer. I can tell you that the strength gets weaker and weaker as we go from south to north. So it's not like this is less south than this one, okay? I don't quite know how to answer that question. Maybe it'll become clearer to you when I show you how this actually becomes magnetic in the first place. On a bar magnet, north, south, weakest in the middle. It gets progressively weaker as we move towards the middle of the magnet. I sprinkle the iron filings on, and again, we'll see that curved line that connects the north and the south poles. We can see that it's much stronger at the poles. It's even sticking up off the page. But there is an attraction here. As I move towards the center, it becomes weaker and weaker down at the center. And these lines are virtually straight across. So if I try to move those filings, the ones at the bottom move easily. As I go up, you can see it hangs on to them more and more until I reach the poles. Next time you see this horseshoe magnet, I'll need you to visualize those lines and how they go across this way. Right? Any question, Matt? If I put them out here, they won't. There's not much of a field out here. There'll be a little bit because it curves out around, but no, you won't have hardly any attraction on the outside of it. Okay? All right. So now the question is, what we're really trying to answer now is, what's the difference between this nail and this permanent magnet? They're both made of iron, and yet this one has a magnetic pole. It has an attraction. This one doesn't do anything. They're both made of iron, so something must be fundamentally different between these two. What is it? There you go. That's pretty darn close. Bill Nye described it yesterday pretty well, so I'm going to play that little clip for you, and then I'll try to show it up here again.
Electrons in iron are spinning. Now, in a piece of iron like this, the electrons are spinning all different directions. But in a magnet that's made of iron, the electrons are all lined up, so that a magnet has a front end and a back end, a north pole and a south pole. Now, what would happen if you could cut a magnet in half? Would you get a magnet that was only a north pole or a magnet that was only a south pole? Well, take a look at this. These are the electron cars of science, and they each have a front end and a back end, a north end and a south end. Now, right now, they're parked all which way, but let's line them up like the electrons in a magnet. Back it up, Joe. Okay, Sally. There. Now, let's cut them in half. See, we end up with two smaller magnets. These cars have a north end and a south end, a north pole and a south pole. So if you break a magnet in half, you get two smaller magnets that each have a north pole and a south pole. Near as we can tell, there's no way to get a magnet with just one pole.
Okay. So we're going to try to build this concept. This is the main concept for today. It can get a little tricky because it requires you to understand how atoms work, to picture electrons, these really tiny things. Let's start big and work our way down. First of all, in order for something to have the ability to become a magnet, it must be made of what three things? Nickel, iron, and cobalt. These materials all have what are called unpaired electrons. These materials all have unpaired electrons and can be made into permanent magnets. These materials all have unpaired electrons and can be made into permanent magnets. That's your definition for nickel, iron, and cobalt. So what we're trying to unlock is how this one's not magnetic and how this one is, and how potentially we can make this magnetic. First thing you have to know is that when we have a magnet, let's say this is one magnet, you break it in half, you get two magnets. You get a north and a south here and a north and a south here. And you can keep breaking that all the way down until you get to a magnet that's 2 atoms big. Okay? 2 atoms. I break it in half, I still have 2 magnets. It's a very, very tiny magnet. It's not going to have much of an effect, but it is a magnet. And this is a magnet. Okay? And if they are working together, they're a stronger magnet. If they're working against each other, fighting against each other, they're weaker. They cancel each other out. Are you with me now? Okay. So first thing we have to do is look at the atoms themselves. If each atom can behave like a magnet, we have to look inside the material and ask ourselves, are those individual magnets working together or not? You saw on what Bill Nye showed up there with the cars, how we got them all to line up facing the same way, parked the same direction. In that example, they were working together like a stack of magnets. And each one helps the next. You still follow this? Okay. If I want to give this nail some magnetic properties, what I might do is take a permanent magnet like this one and stroke the end of the nail in the same direction. Notice I'm not rubbing back and forth. I'm going one direction, lifting off, and doing it again in that same direction. And what I'd like you to be able to do is visualize what's actually happening to the atoms. I'm not changing the atoms. They're not going from being iron to something different. They're still iron. What I'm affecting is the tiniest little things within the atoms, the electrons. And I'm causing the atoms to line up their magnetic fields. I'm getting the cars to park, all facing one way. So now what wasn't magnetic before is now. I passed on that property. Okay?
Can you get the magnetism off?
Yes, so we're going to get to that in a second. Excellent question. So what I just did to this nail, I'm going to illustrate now here. Picture this nail before I rubbed it with the magnet, like you see here. Each atom has magnetism. Each atom is working like a little magnet. But they're not working together. Their magnetic fields are facing in all different directions. They're not helping each other out. And that's why this doesn't appear to be magnetic, because it's not helping itself out. If I now take a permanent magnet and I bring it in there, I'm going to influence those other magnets. They're going to want to start to line up and start to work together. See that? As I bring that around through the material, more and more of these little clumps will form. I formed a clump there, I stroke this part, I form a clump there, and we get these little clumps of atoms that have their fields all lined up. Well, the bigger they are, the more that are working together, the stronger they are. Each of these little clumps are called magnetic domains. It's a clump of atoms where the magnetic fields are all working together, are all aligned. I'll read that for you again. A magnetic domain is formed by the alignment of groups of atoms with unpaired electrons. Formed by the alignment of groups of atoms with unpaired electrons. Formed by the alignment of groups of atoms with unpaired electrons. It's these little clumps that are working together. I keep rubbing the magnet over the top, and I'm taking these and I'm lining them up, okay? Lining those up. I keep moving across, I keep lining them up. And eventually you get all the domains facing the same way, and you make the material magnetic when they're all lined up facing the same way. Does that make sense? Okay. So first, we start with our iron nail that isn't magnetized. Each atom works like a little miniature magnet, okay? And they're randomly arranged. By rubbing a permanent magnet over that, I influence these little individual magnets and I get them to line up in clumps called magnetic domains. I get enough clumps, each clump will influence the one next to it, and they all start doing the same thing. It's like a little gang. They all dress the same, they wear the same jacket, they face the same direction, they do the same thing. We form a little gang of magnetism in the material, okay? Now, we've explained now how that became from random to lined up arrangements, but now we need to look even closer. I said that each atom was like a little miniature magnet. And the thing that makes that atom magnetic is not the protons or neutrons, but the electrons. The truth is, the smallest magnet is a spinning electron. That's like a little miniature magnet, a spinning electron. But since atoms have many electrons around them, what we have to look at is what direction are they spinning. If I have an electron spinning this way, it makes magnetism. If I have another electron in that same atom spinning the opposite way, it makes magnetism, but that magnetism will cancel it out. See what I'm saying? One's going one way, one's going the other way. They cancel each other out. And the atom is not magnetic. That's why things like copper and gold and silver and all the other metals besides iron, nickel, and cobalt, that's why they aren't magnetic. Because they have what we call paired electrons. They won't make miniature magnets because one electron spins one way, the other one spins the opposite, cancels it out. Okay? In material like iron, nickel, and cobalt, each atom has an electron that spins one way, but it doesn't have one that goes the opposite way that cancels it out. So we end up with little individual magnets. How many think they understand? Okay, got a lot of hands that aren't going up. Let's try this again. We'll start from the most basic. Materials that are iron, nickel, or cobalt are made up of miniature magnets, atoms. Those atoms may be aligned, like in a permanent magnet, where they're all facing the same direction, or they could be a random arrangement. When we have a random arrangement, the material is not magnetic, like most pieces of iron you might pick up. If we expose it to a permanent magnet, we get them to line up in little groups called magnetic domains. Enough groups form, they influence those around, and eventually you have one big clump where all the atoms have their magnetic fields facing the same way. In materials that aren't iron, nickel, or cobalt, the atoms are not magnetic because the electrons that make them magnetic have one that cancels it out, one that spins the opposite way. That's why magnetism is caused by unpaired electrons. Iron, nickel, and cobalt do not have another electron to cancel out the magnetism. All right, so Anthony asked how I can take that away. And that's an excellent question. It's something I want you to know the answer to. I gave it the magnetism, now I want to take it away. I want to take the magical properties away. Well, you got to think like a guy for this one. I fixed it, now I want to break it. What do you use to break stuff?
Hammer.
Hammer. Hit it with a hammer, okay? You probably been told before, don't drop a magnet. That's good advice. These tend to shatter when you drop them, but also dropping a magnet will cause it to lose some of its magnetic properties if it doesn't even break. Another trick that helps to loosen up that bond. Remember how we got them all facing the same way? I want them to go back to being random. Another trick would be, how do I get atoms to start to want to loosen up their bonds and move more? Okay, well the problem is, it's not like, does this one attract to that? Does this one attract to that? Yes. So whether I use the north or the south in, I'm still going to have influence over the electrons, over the atoms. And whether I brush this way or I brush the opposite way, it's still going to get them to line up. Some people have said, well, go sideways and go in different directions. Well, if I gave you a comb, and I had you comb your hair this way, most of the hair goes that way. Have you comb it this way, most of it goes that way. You see what I'm saying? You can't keep using the comb, because the comb's the thing that gets them all lined up in the first place. So I can't rub it with a magnet to get rid of the magnetism. But if I vibrate, I give it vibration, I can break up that arrangement. Instead of facing the same way, they all start to scatter and go in different directions. The other secret is heat. Heat will help break up that arrangement. I can heat it, and some of it will go away. Better still, if I heat it and add vibration, I can take away the magnetism. Now that it's heated up, those arrangements are much easier to break. And notice I hit it in random directions. I don't hit it in just one direction. And that will help disturb, break up that attraction. And now it's gone. Okay? So, that also helps answer how this rock became magnetic in the first place too. Because magnetite was molten metal, came from volcanoes. And as it was cooling, it was exposed to a magnetic field. Not a permanent magnet, because those didn't exist. What magnetic field was it exposed to? The Earth's. The Earth's magnetic field influenced these to become magnets. The trick is that that happened all as it was still hot and the rock was cooling. 2 ways to get rid of magnetism you should have in your notes. Heat and vibration. Magnetite is naturally magnetic rock because it's been sitting on the Earth for a long time. Definition for magnetite. A naturally magnetic rock that contains iron and becomes magnetic after resting on the Earth for a long time. Of course, the fact that it was hot, too, is also important. A naturally magnetic rock that became magnetic as it cooled and sat on the Earth for a long time. Naturally magnetic rock that became magnetic as it cooled and sat on the Earth for a long time. Interesting to note that Not only rocks become a little magnetic from sitting on the earth for a while, but so do buildings. Case in point, Empire State Building and Eiffel Tower. Big structures with iron in them, they actually will influence a compass a little bit. They become magnetized simply by being on the earth and being exposed to the earth's magnetism. Now other metal objects like this trash can isn't going to stay magnetized by just sitting on the earth because it's picked up and dumped out every day, and that gives it what? What takes away magnetism? Vibration. That gives it some vibration, and any magnetism that would build up on it anyway would be pretty small. Okay? But these do have a weak magnetic field because of sitting on the earth. All right. I like this part of the story. This is one of the more recent advances in magnetism. And this occurred in 1820. And what's cool about this story is this was a major discovery that made so many of the electronic devices that you guys use today possible. And it was made by a teacher. And it was made in class as the teacher was giving a lecture. Pretty cool. The guy's name is Hans Oersted. Danish teacher. That weird O is part of their alphabet. Oersted. And in 1820, he was doing a lecture for his science class. And he was talking about electricity. He had these old-fashioned batteries called voltaic piles, these big batteries. And he was doing this experiment with electricity. And it was an accident. It was just by chance that he happened to notice something. He noticed, and I'm going to take that off for a second. I'll put it back up. He noticed that when he ran electricity through his wire, here's my wire, there's my battery up here. When he ran electricity through the wire and he had a compass needle nearby, the needle would spin. See that? The needle would react. And we already knew that a compass needle responds to what? What force? Magnetism, like from the earth. But nobody ever thought at that point in time that magnetism had anything to do with electricity. What was so big about this discovery is that electricity is related to magnetism. In fact, when electricity runs through a wire, it creates magnetism. You're going to be making an electromagnet based on that very principle. Motors, speakers, all of those things that use electricity and make magnetism were possible because of this discovery. Very important. Now, if he hadn't discovered it, someone else would have, and someone else in fact did at about the same time. But electricity makes magnetism. That was his big discovery. So again, for your definition for him, you would say in 1820, while preparing a lecture in electricity, Oersted discovered that a current-carrying wire caused a compass needle to move. Conclusion, electricity makes magnetism. Electricity makes magnetism. Huge discovery. Allowed us to build all of our modern electronic devices based on that concept. If you missed one of the other definitions, you have them all up here now.